All right, so this is going to be our walkthrough for the homework assignment titled Delta Epsilon Limits Involving Infinity. And so these aren't all just going to be delta epsilon limits, right? We're going to use delta m, or we're going to use N-Epsilon, or sometimes we'll use N-M proofs. So we use the m instead of an epsilon whenever the limit equals positive or negative infinity. So that's when we use the m. We'll use the n whenever the limit is approaching infinity, like x approaches infinity or x approaches negative infinity. And so then we'll use n and m if it's approaching infinity and equaling infinity or negative infinity. So for the proofs that it equals infinity, these are a little different than the delta epsilon proofs, right? Because what we're trying to show is that I have some function here, and it's not the sketch I'm making is not of the function we're dealing with in this first problem. But the idea is that this function goes up to infinity as we approach some x value over here, right? And so the idea is for any m you choose, no matter how big that m might be, we need to prove that as we approach this number, a here, our function always goes above m. And even if I make m up here, our function should still go above it. And if I make m up here, my function should still go above it as I approach a. So that's the whole idea, is that there's some interval surrounding a, right, a plus delta or a minus delta, such that no matter how large of an m I choose, my function is always going to go above that value. So that's the idea of what we're doing here. So let's see if we can put that into practice here with the first problem. Right? We're looking at a limit as x approaches 3 from the right of 4 over x minus 3. And so for these ones that equal positive infinity, we're always going to start with given m greater than 0. And we'll choose a delta because we're still using delta here since x is approaching 3 from the right. And we still start off with our same suppose statement. Suppose that 0 is less than the absolute value of x minus 3 is less than delta, right? And then we want to see when our function, we want to show that our function, right, 4 over x minus 3 is eventually going to be greater than m, right, where m is going to be something that is eventually written in terms of constants and delta. So that's our goal, but we're not there yet. So what we first need to do is recognize that these ones don't involve an absolute value. So if you're putting an absolute value on here, that's just wrong. Don't do that. Don't put an absolute value on there. And then second, we need to realize that we have an absolute value up here, which means we need to deal with that in some way. Well, the way we deal with that is we recognize that x is approaching 3 from the right. So if x approaches 3 from the right, that means that x is greater than 3. It also means that x minus 3 is greater than 0. And if something inside of an absolute value, like an x minus 3, is positive, then the absolute value of x minus 3 just equals x minus 3. So effectively what we have here is then that x minus 3 is less than delta. And so using that information that x minus 3 is less than delta, we can just take a reciprocal here. 1 over x minus 3 then must be greater than 1 over delta, right? And so if I have 1 over x minus 3 is greater than 1 over delta, that must mean that 4 over x minus 3 is greater than 4 over delta. And, well, now I've got something written over here that's all in terms of constants and delta. So all I need to do is let 4 over delta equal m. We can kind of do that off to the side if we want to see what does delta need to be. Well, that means we just cross multiply. That means delta needs to equal 4 over m. So we'll choose delta to be 4 over m, which gives us 4 over m, which is just m. And so now we've shown that given an m greater than 0, if we choose delta to be 4 over m, then as x approaches 3 from the right, which is what we're doing here, we have a small interval surrounding 3, 3 plus delta and 3 minus delta, then 4 over x minus 3, the function is always greater than n, right, whatever value we might choose. So that's our proof. All right, for our next one here, it's basically the same problem, except that we have a limit as x approaches 3 from the left of 4 over x minus 3. And of course, that's going to equal negative delta. So for this one, we're not going to start with given m greater than 0 because we're approaching negative infinity. So we're going to actually start with m less than 0. So given an m less than 0, we need to choose a delta. Right? And that delta, we could probably have a general idea of what it's going to be, but we'll go through the process. We're going to suppose that 0 is less than the absolute value of x minus 3 is less than delta. Then, and it's no longer an absolute value of our function, it's just 4 over x minus 3. We want to show that 4 over x minus 3 is eventually less than m, right? Because if we're going down to negative infinity, and I pick an m value here, right, to show that the limit is negative infinity, we need to show that we go below that m value that we've chosen, right? No matter how infinitely small that m value is. So what we'll do is just the same kind of thing we did with the previous one. We'll make the note that if x is approaching 3 from the left, then x is less than 3, which means that x minus 3 is less than 0. Well, if x minus 3 is less than 0, then the absolute value of x minus 3 has to be equal to the opposite of x minus 3, right? Because that's the definition of absolute value. If the thing inside of it is negative, then to find the absolute value of it, you take the opposite of it. Well, in this problem, if the absolute value of x minus 3 is less than delta, that means the opposite of x minus 3 is less than delta. Okay? Which means that x minus 3 is greater than negative delta, or 1 over x minus 3 is less than negative 1 over delta. And so we're going through this process to put x minus 3 in the denominator because we've got an x minus 3 in our denominator over here. And so now we know that 4 over x minus 3 should then be less than negative 4 over delta. And from there, since now we're all in terms of constants and deltas, well, then we can just replace the negative 4 over delta with m, right? If we let negative 4 over delta equal m, that tells us that delta is equal to negative 4 over m. So this is less than, this is equal to negative 4 over negative 4 over m, which is just equal to m. So we want to choose delta to be negative 4 over m. And you might be a little wary of choosing a value for delta that seems to be negative, right? Because I think I've told you in the past that the delta always has to be a positive number. But remember that m is also negative. So if m is negative, right, we've given an m less than 0. If m is negative, then negative 4 over m is actually a positive number. So we'd have chosen a positive delta, which was one of the constraints of doing these problems, is that delta always has to be positive. All right, for our next one here, similar problem. We have a limit as x approaches 3 from the right of 4x over x minus 3 equals infinity. So again, this one is equaling infinity, so it's going to be a delta m proof. So we'll be given an m, in this case, greater than 0 because it's equaling infinity. We want to choose delta, which we need to figure out what that delta is. Supposing the same thing as usual, suppose that 0 is less than the absolute value of x minus 3 is less than delta, right? Then we need to show that our function, and not the absolute value of our function, just our function, right, 4x over x minus 3, is always greater than something, right? In terms of constants and delta. And so, again, we have an absolute value in the suppose statement, but we don't have an absolute value in our function. So what we want to start off by doing is, again, recognizing that as x approaches 3 from the right, x is greater than 3, or x minus 3 is greater than 0. And if x minus 3 is greater than 0, then the absolute value of x minus 3 is just equal to x minus 3, which tells us from right here that x minus 3 is less than delta, or 1 over x minus 3 is greater than 1 over delta. So we can say that 4x over x minus 3 must be greater than 4x over delta. Now, this is exactly what we did in problem 1, and really pretty much the same thing as what we did in problem 2, but this time we still have an x in there, so I can't just immediately set that equal to m. Well, we then just have to use a little bit of information that we have that as x approaches 3, x is greater than 3. Well, if x is greater than 3, then 4x must be greater than 12. Right? And if 4x is greater than 12, then 4x over delta must be greater than 12 over delta. And so now we have this all in terms of constants and delta, so we can just replace it with m. So if 12 over delta is going to be equal to m, then delta is going to be equal to 12 over m. And so we've now shown that if we choose delta to be 12 over m, right, then our function is always greater than m. And of course, we could have chose, something else here. We could have said that like 4x over delta, not just greater than 12 over delta, but we could have chosen, it must be greater than 10 over delta, or 3 over delta, or 1 over delta if we wanted to, right? Because 4 times 3, which is 12, right, is clearly more than 1 also. It's the closest thing that it's greater than that we know, like the largest number that we know it's greater than is going to be 12, but we could have picked anything smaller than that as long as it was a positive value as well. And we could have done that with the first problem and with the second problem also. All right, for number 4 here, we're going to just kind of use the same basic idea. We're going to say given an epsilon, or not given an epsilon, given an m, you get used to doing these epsilons. Given m greater than 0, we want to choose delta to be equal to something. We'll figure out what that is. Supposing that this time we have 0 is less than the absolute value of x minus 2 is less than delta, then we want to show that our function x squared over 2x minus 4 is eventually greater than m. And so this time we'll note that the thing in our denominator, right, is 2x minus 4, which is not quite the same thing as the x minus 2 that we have up in our suppose statement. But if we factor out a 2 from that, we can see that we just have 2 times that x minus 2 that is what is in the absolute value of our suppose statement. So that's okay. So we'll do that same work off to the side as we've done previously. We'll just say as x approaches 2 from the right, x must be greater than 2, which means that x minus 2 must be greater than 0, which means that the absolute value of x minus 2 is equal to x minus 2, which means from here that x minus 2 is less than delta, or 1 over x minus 2 is greater than 1 over delta. So we can then just say that this is greater than x squared over 2 times delta, because we're just multiplying this statement over here by x squared over 2, which we know is always positive, so it's okay to multiply something that's in an inequality by stuff that's always positive. So basically what we've done is these two statements are just reflections of each other here, just multiplied by x squared over 2 on the left. And so that's why we're allowed to do that. So now that we've got that, we just need to figure out what x squared is greater than. Well, if x is greater than 2, then x squared sure must be greater than 4. So this would be greater than 4 over 2 delta. Well, 4 over 2 delta is just 2 over delta. And you don't have to say anything more than that. You can just turn that into your m. But if you want to, like we said in the last one, right, 2 over delta must be greater than 1 over delta if you want to. So you could just say that that's true. And then you could say that's equal to 1 over m, which is equal to m. So you can choose delta to be 1 over m here, or you could have chosen delta to be 2 over m here. That would have been fine as well. Or even 1.5 over m, as long as it's something, that 2 is greater than that thing. Again, you don't have to do this. If you left yours as 2 over m, which is probably what I even did in the answer key for it, there's nothing wrong with that. Just noting that you might end up with a slightly different looking answer than what I have in the answer key. And that doesn't necessarily mean it's wrong. All right, for our next one here, we have a limit as x approaches 1 from the left of 5x squared over 6x minus 6. And it equals negative infinity, which means that instead of having m greater than 0, we're going to have m less than 0. So given an m less than 0, we're going to choose a delta equal to something, which we'll figure out. And we'll suppose that 0 is less than the absolute value of x minus 1 is less than delta. Then we need to prove that our function, 5x squared over 6x minus 6, is always eventually less than m. Because again, this one is going to negative infinity, so we want to show that our function goes below whatever negative number we thought our limit might be. So we'll do the same beginning of the side work that we've done with all the previous ones here. Right? We'll say that since x is approaching 1 from the left, x must be less than 1, which means that x minus 1 is less than 0, which means that the absolute value of x minus 1 is actually equal to the opposite of x minus 1 this time, because when you take the absolute value of a negative thing, you take the opposite of it. So that tells us that from this statement here, the opposite of x minus 1 is less than delta, or x minus 1 is greater than negative delta, or 1 over x minus 1 is less than negative 1 over delta, which is perfect because that's really what we need here, right? We're going to rewrite this as 5x squared over 6 times x minus 1, and then we can replace that 1 over x minus 1 just with a negative 1 over delta. Right? And so this is less than 5x squared over 6 times negative delta. Right? And it's okay to do that because if I take this inequality here and multiply it by 5x squared over 6, 5x squared over 6 is always positive. So when I multiply it, that doesn't flip our inequality sign or anything. And so we just get the statement that 5x squared over 6 times x minus 1 is less than 5x squared over 6 times negative delta. So from there, then, we might be tempted to say, oh, well, x is less than 1, which means that x squared is also less than 1. But the problem with that is if I use x squared is less than 1, what we're looking at here now is actually a negative number, right? And so I'm going to write this out a little bit here. We're going to erase some of what we're doing, but right, if we just go down here and say x is less than 1, then x squared is less than 1, I can't take the inequality that x squared is less than 1 and multiply it by 5 over negative 6 delta, right? I can't multiply both sides of this by 5 over negative 6 delta and retain this less than sign, right? It'll flip to become a greater than sign because I'm multiplying both sides of an inequality by something that's negative, right? So knowing that x squared is less than 1 is actually not helpful in this problem. We actually need to know something that x squared is greater than, because then if we know something that x squared is greater than, then when I multiply it by this negative, this 5 over negative 6 delta, it'll flip the inequality sign to be a negative, which is exactly what we need. So what we'll do is we'll just sort of go back here, and instead of doing this x squared is less than 1, which is true, but not useful to it, what we'll do is we'll put an extra little constraint on here. So as we're approaching 1 from the left-hand side, we should be able to say that, well, let's just say that x is, we know that x is less than 1. Let's say that x must be greater than 1/2. And you could pick something like a 4th or a 3rd or 2/5 or whatever value you choose there. It doesn't really matter. And of course, just like with our regular delta epsilon proofs, now we're going to have to say it's going to be a minimum between 1/2 and something else, whatever we end up with in the end, right? Because we've now put this extra constraint on that we had to be more than 1/2 for this thing, right? So, now what we can do here is now we can square these things, and if x is between 1 and 1/2, when I square it, I get x squared, right, is less than 1, but also greater than 1/4. And so now if I take the part that says x squared is greater than 1/4, and I multiply both sides of it by this term we were talking about before, the 5 over -6 delta, we end up with 5x squared over -6 delta is less than 5 over 6 times 4 times that negative delta, right? Which is exactly the kind of statement that we wanted, right? So we can now say, this is all just kind of side work, we could say this is less than -5 over 24 delta. And now once we have that, we can immediately go in and say, well, now that's all in terms of constants and delta. So let's just let -5 over 24 delta equal m, which means that delta needs to be -5 over 24 m. So this is equal to -5 over 24 times -5 over 24m, which is just m. So we want to choose the minimum between 1/2 and -5 over 24m. So this one's a little bit tricky. The ones where it's negative infinities tend to get a little bit trickier than the other ones. So just be extra careful with those. All right, our next one here, we have a limit as x approaches 5 from the right of x cubed over 5 minus x is equal to -infinity. And so we'll start the same way. We'll say given, and again, this one is m is less than 0. We're going to choose a delta, and m is less than 0 because the limit equals -infinity. So choosing a delta here for this, we'll suppose that, just like all the other ones, that 0 is less than the absolute value of x minus 5 is less than delta. Then our function, x cubed over 5 minus x, right, not in absolute values, right, because we don't need that anymore, is eventually less than n. And so we'll just kind of start off with our same side work here that we've been doing. Right? If x is approaching 5 from the right, then x is greater than 5. Which means that x minus 5 is greater than 0, which means that the absolute value of x minus 5 is just x minus 5. And from there, that tells us that x minus 5 is less than delta, right? Well, we don't have x minus 5, though, in our problem over here. We have a 5 minus x. So I could factor a negative sign out of this to get -5 minus x is less than delta, or that 5 minus x is greater than negative delta, or 1 over 5 minus x is less than -1 over delta. And now I can replace in here, right, with a less than sign, x cubed over a negative delta. Right? And x cubed, as we approach 5 from the right-hand side, is always positive, so we don't need to worry about multiplying by the x cubed and messing with the inequality sign there. So then from there, we've got x is greater than 5, right? And that tells us that x cubed, maybe we'll note this up here. If x is greater than 5, x cubed is greater than 125, which seems like that's a problem, right? Because if I wanted to replace that x cubed with a 125, we'd have to say greater than here. But in reality, we actually don't need to do that, because if I know that x cubed is greater than 125, if I divide both sides of this by a negative delta, that'll flip the inequality sign. So I can say that x cubed over negative delta is less than 125 over negative delta, right? Because that flips the inequality sign when we divide by a negative delta, since delta is always a positive value. And now we're done. We can just say this is equal to, and maybe we want to do the work off to the side, where we have 125 over negative delta is going to be our m. That means that delta is going to be negative 125 over m. So this is the same as 125 over negative 125 over m, which is just m. So we'll choose delta to be, and I got to get rid of this here. Delta will be equal to, we had negative 125 over n. So hopefully that's a fairly good introduction to how we do these limits that equal infinity or equal negative infinity. So now we're going to do a couple where the limit is as x approaches infinity or as x approaches negative infinity. And so for these, we're still going to start off with equaling a real number, right? So we're equaling 0 here, right? Which is certainly a real number. And so what that means is we're showing that there's a horizontal asymptote, which effectively means as I approach infinity, right? And this is not necessarily what this function looks like. We're coming down here to this horizontal asymptote of y equals 0. And what we want to show is that there is a range of epsilon values above this limit and below this limit of 0, that eventually, after some value of n, my function always sits between those two horizontal lines, L plus epsilon and L minus epsilon. Right? And so it's very similar to how we were doing the original delta epsilon limits, except that we're not approaching from both sides. We're saying once we get past a certain point, once we get past this n, the function always sits between those horizontal lines, rather than as we approach from both sides, it's always between those lines. And because now we're not approaching from both sides, we're just approaching infinity. All right, so the setup is going to be, again, pretty similar. We're back to using epsilons now, though, because this is a limit that equals a real number. So given an epsilon greater than 0, we're now going to choose an n, right? And we always use n when we're talking about these limits that as x approaches infinity or negative infinity. We'll still suppose, though, something different now. So now we're going to suppose that x is greater than n, which is greater than 0. And if I suppose that x is greater than n is greater than 0, that means I'm supposing that the x value we're looking at is bigger than that number n that we said. Right? And we want to then show that, and again, this one now is going to have to be an absolute value. We want to show that the absolute value of our function minus our limit is always eventually less than epsilon, where epsilon is written all in terms of constants and n's. So let's see if we can get to that point. We can immediately just eliminate that minus 0, just make this 1 over x plus 3. Right? And then, well, then we need to just kind of build in an x plus 3. And we also need to think about what we know about this limit. This limit is as x approaches infinity. Right? So if x is approaching infinity, we know that we're going to have positive x values eventually. Right? And as long as x is greater than negative 3, then our function here, the 1 over x plus 3, is always positive. Right? And if we're approaching infinity, then x is going to be greater than negative 3. So if we'll say as x approaches infinity, x is certainly greater than negative 3, which means that x plus 3 is greater than 0. which means that the absolute value of 1 over x plus 3 is just the same as 1 over x plus 3. Now, sometimes we might make a note here that like x has to be greater than -3. So we might, in our choose, say we're going to choose n equal to the maximum of -3 and something else. But n is always defined as positive anyway here for our problem, so we don't really need to worry about that maximum. So now that we have that the absolute value of 1 over x plus 3 is just equal to 1 over x plus 3, we should be able to find a relationship between 1 over x plus 3 and n, right? Because we know that x is greater than n. That was written out for us at the beginning. X is greater than n, which means that x plus 3 must be greater than n plus 3. We just add 3 to both sides. And then we can just take the reciprocals and say 1 over x plus 3 must be less than 1 over n plus 3, which is exactly what we wanted. We wanted our function to be less than something in terms of constants and n. So we have that our thing, 1 over x plus 3, is now less than 1 over n plus 3. And from here, we can make an adjustment to this, or we can just immediately replace this with an epsilon. So I think it's nicer to just kind of clean this up a little bit. I can say this is less than 1 over n, because if I have a larger denominator over here, that's going to yield a smaller thing, right? So a larger denominator like n plus 3, if I take 1 and divide it by that thing, it should be less than 1 divided by a smaller thing, right? So 1 over n plus 3 should be less than 1 over n, and then we can just rewrite this. We can say, well, 1 over n is equal to epsilon, which means that n is equal to 1 over epsilon. So we can say this is equal to 1 over epsilon, which is just epsilon. So we'll choose n is equal to 1 over epsilon. And that should be our final answer for this one. All right, so this next one looks very similar to the last one that we were doing, but instead of approaching infinity, now we're approaching negative infinity, which means that we're going to start off in the exact same way. We're just going to start off given an epsilon greater than 0 because our limit is still equaling a real number. But now we're going to choose our n, but we're going to have a slightly different supposed statement. Our supposed statement is going to be supposing that x is less than n is less than 0, which makes sense, right? Because x is going to be approaching negative infinity, so we have to be using negative numbers for this. We can't be using positive numbers for this. And so that's going to kind of like flip all the inequalities that we were dealing with last time around. And so our then statement is going to start off the same. It's just going to be then the absolute value of f of x minus the limit is eventually less than epsilon. And so we'll rewrite this as just the absolute value of 1 over x plus 3. But then we'll need to figure out how we can pull that x plus 3 out of the absolute value, right? And so we know that if x is less than -3, then x plus 3 is less than 0. So if x plus 3 is less than 0, then 1 over x plus 3 is also less than 0, which would tell me that the absolute value of 1 over x plus 3 should equal the opposite of 1 over x plus 3. So we're going to say that this is equal to the opposite of 1 over x plus 3, so long as we let x be less than -3. Well, if x is less than -3, then we kind of want to put a minimum constraint then here on n to be -3, right? So the lowest our value for n could be really is -3. And in fact, really, like it can't even really be -3, but we're just going to, if x is less than -3, it can't be -3. But since we're supposing that x is less than -3, we can build that into our answer by putting the constraint on that n is at a minimum -3, and that means that x will always be less than -3. And so now we've got -1 over x plus 3. Well, -1 over x plus 3, we should be able to then just go in and say that since we know x is less than n, that x plus 3 is less than n plus 3, or that 1 over x plus 3 is greater than 1 over n plus 3. And if I multiply both of those by a negative sign, it'll flip the inequality sign again, which means that -1 over x plus 3, which is what I have up there, should be less than -1 over n plus 3. And so we could at this point do the same kind of thing that I did with the last problem, where we break this down and make it a little bit simpler, but this time I think I'm just going to leave it as is. I'm just going to let -1 over n plus 3 equal epsilon, because that's now in terms of constants in n, which means I can replace it with the epsilon. So that's going to tell me that -1 over epsilon is equal to n plus 3 if I just cross multiply, or that n should be equal to -3 minus 1 over epsilon. So we'll just say this is equal to -1 over our n, which is -3 minus 1 over epsilon, plus 3, which is just epsilon. And so our n value is the minimum between -3 and -3 minus 1 over epsilon. And that should be our final answer. And we should be able to see also that there's not really a need for that minimum of -3, because if epsilon is a positive number, which we know it is, we know that -3 minus 1 over epsilon is always going to be less than -3. So in fact, we can really just, it's good to put that restriction on from the start, but then we can recognize here that this is always less than the restriction that we put on. So n really should just be -3 minus 1 over epsilon without that extra constraint. All right, for our next one here, we have a limit as x approaches infinity, so another n proof of 3x over x plus 5 is equal to 3. So it equals a real number. So this is going to be an N-Epsilon proof. And we'll start with given an epsilon greater than 0. We want to choose n equal to something, right? And so if n is, or x is approaching infinity, that means that x is greater than n is greater than 0. So that's what we're supposing here. Suppose we have positive x values, so a positive n. Then the absolute value of our function, 3x over x plus 5 minus its limit, which is 3, should eventually be less than epsilon. So we'll start off by simplifying down what's inside the absolute value by getting a common denominator. So we have 3x over x plus 5 minus 3 times x plus 5 over x plus 5. And if we simplify that, the 3x minus the 3x there is going to cancel, and we're just going to be left with, inside the absolute value, a -15 over x plus 5. Right, so we have -15 over x plus 5. And if x is going towards infinity, then the 15 and the x plus 5 is all positive, and we're just left with a negative. Well, the absolute value of a negative value is just the positive value of it. So I can just clear that out of the absolute value by eliminating the negative side, because I know 15 over x plus 5 is always positive. Right, so now we've simplified down our absolute value expression into just 15 over x plus 5. And now we'll just use the information that we knew that x is greater than n to say that x plus 5 is greater than n plus 5 by adding 5 to both sides. And if we do that, then we know that 1 over x plus 5 is less than 1 over n plus 5. And so I can then just replace my 15 over x plus 5 and say that that is less than 15 over n plus 5. And so once we have that, we can leave it in that form if we want to, or since we know that n plus 5 is a larger number than n, we can say that this is less than 15 over n, because if I divide by something bigger, I should get a smaller number. And so I could rewrite it this way to just simplify things a bit. You don't have to do that, but I think I will. And we'll have 15 over n is now equal to our epsilon, which means that n is equal to 15 over epsilon. So 15 over n is equal to 15 over 15 over epsilon, which is just epsilon. And so our n that we choose is 15 over epsilon. All right, for number 10 here, again, we are approaching negative infinity, but it equals a real number. So this is another N-Epsilon proof. And we're going to say given an epsilon greater than 0, we'll choose an n. And we'll suppose, again, this time that x is less than n is less than 0. Then the absolute value of our function minus the limit needs to eventually be less than epsilon. So just like with the last one, we'll simplify the expression inside the absolute value first by getting a common denominator. So that'll be 3 times x squared minus 1 minus 1 times 3x squared plus 1 over 3 times 3x squared plus 1 in the denominator, which, if we try to simplify that out, we get a 3x squared minus a 3x squared. So those will cancel. And we get a minus 3 minus a 1, which should be a negative 4. So we have negative 4 over 3 times 3x squared plus 1, all inside of an absolute value. Well, 3x squared plus 1 is positive no matter what. And so then we really just have a negative inside of that absolute value, which we can clear off by just getting rid of the negative. So the absolute value of negative 4 over 3 times 3x squared plus 1 is the same as just 4 over 3 times 3x squared plus 1. And so now we want to show that that is less than epsilon. And so the way we'll do that is, since we just have a singular term there in the denominator, we'll just use that expression that we have, that x is less than n, and we'll just build a 3x squared plus 1 out of that. So first we'll square it. Right? If x is less than n, right, then that means that if x, which is a negative number, gets squared, right, that means that x squared is going to be greater than n squared. Like, for example, if x is negative 2, right, that's less than negative 1, right, since we know that these are both negative numbers from our original statement. When I square them, that inequality sign should flip. Right? 4 should be greater than 1. Right? X squared should be greater than n squared. So we have x squared is greater than n squared. And then now I can just, since they're positive numbers, it's easy to deal with. I'll just multiply by 3 and add 1. So 3x squared is greater than 3n squared. And 3x squared plus 1 is greater than 3n squared plus 1. And now 1 over 3x squared plus 1 is less than 1 over 3n squared plus 1. So this should be less than 4 over 3 times 3n squared plus 1. And so we can distribute out that denominator. We could just solve right from here, but I think it's nicer to just distribute out this denominator. This is the same as 4 over 9n squared plus 3. And again, if I have 4 over 9n squared plus 3, that should be less than something that has a smaller denominator. So this should be less than 4 over 9n squared. Right? And again, if I'm multiplying n squared by 9, that's going to be bigger than if I don't multiply n squared by 9 in the denominator. So I can say this is less than just 4 over n squared. And so now, that seems simple enough. That's pretty straightforward to deal with. We'll just let 4 over n squared equal our epsilon, which means that n is going to equal the square root, either positive or negative square root, of 4 over epsilon. Well, then we have to think about which one of those we want to choose. And we said up at the top that n must be less than 0, which means we need to choose the negative square root down here. We cannot choose the positive square root. we'll choose the negative square root. So this should now be equal to 4 over negative root 4 over epsilon squared, which is just epsilon. And so our choice for n should be negative square root of 4 over epsilon. All right, for our next one, again, we have a limit as x approaches infinity, and it's equal to a real number again. So this will be an N-Epsilon proof. So given an epsilon greater than 0, we'll choose n equal to something, and we'll figure out what that is in a second. We'll suppose that x is greater than n is greater than 0 this time because x is approaching positive infinity. And then we'll have the absolute value of 2x over x squared plus 1 minus 0 eventually needs to be less than epsilon, which is just an absolute value of 2x over x squared plus 1. And because we know that x is approaching infinity, right, 2x is certainly positive, and x squared plus 1 we know is always positive, so we can just eliminate the absolute value here to turn this into 2x over x squared plus 1. So from there, we will just make a couple little quick jumps, right? If I have 2x over x squared plus 1, well, that should be less than 2x over x squared, right? Because if I have, like we've done in a few of the other problems, if I have a larger denominator, right, x squared plus 1 is a bigger number than x squared, well, that means that if I divide by it, I end up with a smaller number. So 2x over x squared plus 1 should be less than 2x over x squared. And 2x over x squared just simplifies down to 2 over x. And we can just cancel out the x's. And if x is greater than n, then 1 over x is less than 1 over n, which means that 2 over x is less than 2 over n. And if 2 over x is less than 2 over n, then that means we're done. Right? All we have to do is say that 2 over n is equal to our epsilon, which means that n is equal to 2 over epsilon. So we get 2 over epsilon, which is just epsilon. So our choice for n is 2 over epsilon. All right, for number 12 here, we have a limit as x approaches infinity of 4x squared over x plus 3 is equal to infinity. So this is an n-m proof. So we're combining the idea of the n, where we're picking an x value, all of our x values are greater than some n, which are all positive, is equaling infinity, which means that we're picking an m value that we're showing our function is always greater than. So we'll start this one off with given an m greater than 0. And again, if we were equaling negative infinity, it'd be an m less than 0. And then we'll choose an n equal to something. And so we'll see what that becomes in just a second. We'll suppose that x is greater than n is greater than 0. Then we no longer need an absolute value. It's just 4x squared over x plus 3 needs to eventually be greater than n. So we need to show that 4x squared over x plus 3 is greater than something that is all in terms of constants and n. And so what we'll do is we'll just make a little note here that if x is greater than 3, right, and I'm choosing 3 strategically, you're going to see why, because of this 3 down here, then x plus x must be greater than x plus 3. Now, if I put the constraint that x is greater than 3, then I need to put in a maximum here of 3. And so if I say that x is greater than 3, then x plus x, which is the same as 2x, must be greater than x plus 3. And the strategy here to do this is so that we can get a singular term in our denominator that involves x's. Right? Because if I have a singular term in my denominator with an x in it, then I should be able to cancel the x with the 4x squared. So if 2x is greater than x plus 3, right, well, then that should tell us that 1 over 2x is less than 1 over x plus 3, which if I write this in the opposite way, I have 1 over x plus 3 is greater than 1 over 2x if I just flip the sides of those and flip the inequality sign like we should. So this should be greater than 4x squared over 2x. Well, 4x squared over 2x is just the same as 2 over x. And so I know that now my function is greater than 2 over x, as long as x is greater than 3, which we can put that constraint on it because x is approaching infinity. So now we can just say, well, if this is 2 over x and x is greater than n, right? Well, if x is greater than n, we should be able, oh, this is not 2 over x. This is equal to 2x. Be careful there. Right, 4x squared over 2x is certainly equal to 2x, not 2 over x. So if x is greater than n, then 2x is greater than 2n, right? And that means that 2x is greater than 2n, and 2n, even if we want to, we can say is just greater than n, and so we can just let that be our n. So we'll just choose n to be the maximum between 3 and n. So yeah, be careful with your simplification there. I don't know why I said that was 2 over x, but that's just 2x. And so our goal here, we should see, was to get the x's in the numerator for this. Because if the x's are in the numerator, then I can use this inequality, x greater than n, to just kind of go straight into from x's to n's. If I've got x's in the denominator, like I accidentally tried to do there, we wouldn't be able to use that x greater than n inequality. And we would, because then we would have to take the reciprocal and get 1 over x is less than 1 over n. So if we were trying to show that this is equal to it needs to be less than something, then we might want to get those x's into the denominator rather than the numerator. So for this next one, we have a limit as x approaches negative infinity of a function is equal to negative infinity, which means that it's going to be an n-m proof, which means we're going to start with given m less than 0, and we'll choose an n equal to something. Right? And we're choosing m less than 0 because the limit equals negative infinity. And then we're going to suppose that x is less than n is less than 0 because x is approaching negative infinity. Then we need to show that our function x cubed plus 1 over x squared plus 1 is eventually less than m, where m is written all in terms of constants and n. So we may not have a good idea of where to start with this, but what we're going to do is we're going to put like this little extra constraint right now that x is going to be less than n is going to be less than negative 1. And the reason I'm doing that is if x is less than negative 1, then I know that x squared is greater than 1. And then we can use this little trick that we did with the last one, where we added the x squared in to both sides. Last time we just added an x to both sides. But if I add an x squared to both sides, I get 2x squared is greater than x squared plus 1, which means that 1 over 2x squared is less than 1 over x squared plus 1. Or that 1 over x squared plus 1 is greater than 1 over 2x squared, which doesn't seem to be what I want here. But if x is less than negative 1, then that also tells me that x cubed is less than negative 1, which means that x cubed must be a negative number that's less than negative 1, and that x cubed plus 1, which is my numerator, is less than 0, which means that if I take 1 over x squared plus 1 greater than 1 over 2x squared, and I multiply both the top and the bottom by a negative number, which is x cubed plus 1, I should now get that x cubed plus 1 over x squared plus 1 is less than x cubed plus 1 over 2x squared. So that gives us a little bit of a start. And then now what we're going to do is we're just going to use another little trick here, that if I'm adding a 1 into that, right, then I could also replace that 1 with something that I know is more than 1. Right? And if I put in something that is more than 1 up into the place of that 1, then that numerator seems like it's getting to be a bigger thing, but since it's a negative value, it's actually becoming, or it is, even though it's a negative value, it's becoming a larger thing in that numerator. So I can replace that 1 with something that I know is more than 1. And something that I know is more than 1 is x squared. So I can say that this is less than x cubed plus something more than 1, x squared, over 2x squared. And the reason for doing that is to factor out the x squared from the numerator so that it'll cancel with the x squared that's in the denominator. And so I can do that cancellation and just say this is the same as x plus 1 over 2. Well, if x is less than n, then x plus 1 over 2 should be less than n plus 1 over 2. And so now I can just call that my m. I'll just say n plus 1 over 2 is equal to m, which means that n should be equal to 2m minus 1. So this is equal to 2m minus 1 plus 1 over 2, which is just m. And so now we're going to choose n to be the minimum of negative 1 and 2m minus 1. And for our last one here, it's again an n-m proof. We're going to be given, again, this time an m less than 0, right, because we're equaling negative infinity. And we'll choose an n equal to something here. And we'll suppose that this time x is greater than n is greater than 0, because x is approaching infinity. Then our function 2x squared plus 5 over 4 minus x needs to eventually be less than n. And so if we are approaching infinity, we could say that x needs to be greater than n being greater than 4. If we put that extra constraint on this, then what we'll want to do is we're going to choose n to be a max between 4 and something else. But the reason I'm doing that is so that I can manipulate that 4 minus x. Right? So if I have x greater than 4, then I know that 2x squared plus 5 over 4 minus x has got to be less than 2x squared plus 5 over just negative x, right? Because what I'm doing there is I'm making that denominator go from 4 minus x to a negative x, which makes that denominator a smaller value, right? And my denominator is a smaller value. If we're dividing by something smaller, usually we get something that is bigger, right? And so that's what we've got here, 2x squared plus 5 over the negative x. And we can do the same thing with our numerator. If we make our numerator smaller here, then we should be making, and normally if we make our numerator smaller, we're making something that is a smaller thing, right? And so if we replace that 2x squared plus 5 with something that it is smaller than, something smaller than it, it's just 2x squared, so we end up with 2x squared over the opposite of x, which we should just be able to simplify down into negative 2x. And if x is greater than n, right, then 2x is greater than 2n, and negative 2x is less than negative 2n, right, which tells me that I can rewrite that as negative 2n. And if we end up with a negative 2n there, that means we're basically done. We just let negative 2n equal m, which means that n is going to equal negative m over 2. So this is equal to negative 2 times negative m over 2, which is just equal to m. So we want to choose n to be the maximum between 4 and negative m over 2. And that's the end of the walkthrough here for the delta epsilon limits involving infinity. Probably have one more assignment at the end of the unit with more limit proofs just to practice all the different types, but that's it for this one.